Have you ever made a lot of sandwiches for your friends? If you open that loaf of bread and you open that package of cheese and that package of ham and you start slapping sandwiches together, you know how it's kind of cool it all comes out even in the end? No, of course not. It never comes out even in the end. You always run out of one thing while you've still got some of the other things left. And it's the same way in chemistry, that if you're actually doing a real experiment, running a real reaction, you're probably not going to have exactly what we call stoichiometric amounts. Stoichiometric amounts means that you would have the exact right number of moles of each of the two reactants to react together so that there were no leftovers at the end. It would be like making all those sandwiches and coming to the last sandwich and having exactly the amount of bread and cheese and meat that you need to make that last sandwich, and you don't have any leftovers. And that very rarely happens in real life. So what we're going to look at now is a little bit more realistic scenario where we're just going to be given the amount of each of the reactants that's going to go into this process. And we're going to look at figuring out which one of these reactants will run out first, because that will be called the limiting reactant. If it runs out, then the reaction stops, and that event limits the amount of product you can make. That's why we call it the limiting reactant, the one that runs out first. And it's not always the one that's present in the lesser amount, because as you know, in a chemical reaction, sometimes you need more moles of one thing than the other thing to run the reaction. So let's look for an example at the reaction we have on the board. You've seen this reaction lots of times before. We've got nitrogen and hydrogen combining to make ammonia. Now we are actually going to be told at the very beginning of this problem how much nitrogen we started with, how much hydrogen we started with, and in this case we're also going to be told how much product we were able to recover. In other words, how much product we captured that we could use again. So our first job is to figure out which one of these reactants is the limiting reactant, which one ran out first, because that will tell us that maybe mixed in with our product, we're going to have some leftover something else. Whichever one gets left over is going to be mixed in with a product, and we would need to know about that. So we want to know which one of these might have leftovers. And then we also want to calculate how much product do we expect that we should get, knowing that we might not actually be able to collect it all in a reasonable form that we could use. So we'll figure out how much we should be able to get, and then we'll take the amount we actually got and figure out what we call a percent yield. So let's run through this problem. First of all, we want to take each of these two things and we're going to set up a scenario very similar to what you've already been doing, except that we're going to do it with both of them. So watch what happens here. First, we'll take nitrogen, and then we'll take hydrogen. So nitrogen, we've got 15 grams. And you know the first step with these things is always to convert them to moles and then do a mole ratio to figure out how many moles of product we can make. So we'll divide that by 28 grams per mole. We'll do a mole ratio. We can make 2 ammonias for every 1 nitrogen. We'll do that. And then I'm actually going to stop there and calculate moles, because that's really as far as we have to go to figure out which one of these things is going to run out first. Okay, hydrogen, we've got 15 grams again. And this one has a much smaller molar mass. And then we have a ratio of 2 ammonias for every 3 hydrogens. So we can make 2 ammonias for every 3 hydrogens. All right, let's do the math here, and then we'll talk about what it means. So 15 divided by 28, and then times 2, gives us 1.07. Okay, so this is moles of ammonia. If we use all the nitrogen, we can make this many moles of ammonia. So 15, well, I guess these cancel, so 15 divided by 3 is 5. Now this is also moles of ammonia. If we used all our hydrogen, we could make 5 moles of ammonia. Now here's what happens. After we make 1.07 moles of ammonia, the reaction stops. because at that point we've run out of nitrogen. We only have enough nitrogen to make this much ammonia. So we can't make this much. We're going to have leftover hydrogen. So the first thing I'm going to do here is circle this, and LR stands for limiting reactant. I'm going to say that is my limiting reactant. Nitrogen limits the amount of product I can make. The reaction stops when the nitrogen gets used up. So what I know at this point is that I actually can make 1.07 moles of ammonia, and that's it. So as part of the problem, we will want to say then, how many grams of ammonia would we expect to be able to make? So we'll take the moles of ammonia, multiply it times its molar mass, because the molar mass of ammonia is 17, so 1.07 times 17 gives us 18.2. And we will say that that is the expected yield. We would expect this reaction to yield 18.2 grams of NH3 using the same procedure that you've been using before. See, we converted to moles, we multiplied by a mole ratio, and then we multiplied by the molar mass of NH3. Now we had to go through this process with both of them to figure out which one limits the amount of product, and therefore to figure out which one needs to get multiplied by its molar mass. So we can't make 5 moles of product, so we just scratch that because this will run out first. Alright, now what I'm doing on this video is actually covering 2 sections of what we'll do in class. We will stop section 5 at this point, and you'll get lots of practice doing that. But for the sake of not having too many videos, I'm going to go ahead and do the next step, so you can stop here if you don't want to go any further. But in the next step, we would be told how much product was actually made, and our actual yield is 10.5. And we want to express our yield as a percent of what we thought we should be able to get. So we actually got this. We calculated we should be able to get that. So doing a percentage, this is the part and this is the whole. So we only got about 10/18 of what we should have been able to get. So let's do a calculation that gives us the exact percentage. So that is only about 57.7%. Looks like I have 3 sig figs here. Yeah. So not that great, really. Only a little over half of the product that we thought we should be able to get was actually recovered when we did this experiment. And you'll find that quite often, and you'll find this in the lab too because we'll do an experiment, quite often you really don't collect as much product as you think you should because somewhere along the way in the procedure some of it's lost, and that's not uncommon.